Today, we're testing a DIY accelerometer made from a very special kind of apple, a McIntosh. So, what is an accelerometer? It's a sensor that measures acceleration. Basically, how fast something speeds up or slows down. They're used in all kinds of things, like rockets, cars, and even to track your movements in fitness devices. So, how can a sensor measure acceleration? Well, when something with a mass is accelerated, there is a force involved. You might remember the classic equation. Force equals mass times acceleration. F equals ma. One everyday example? Gravitational acceleration. The same mysterious force that inspired Newton to think deeply about physics. That's why we decided to use an apple, out of respect for Newton. Okay, let's explain the principle. Picture this. You're in an elevator, holding an apple with a spring scale. The elevator starts moving upward with some acceleration. Let's call it A. Guess what happens? The apple feels heavier and the spring scale stretches more. That's because the apple is experiencing a greater force, thanks to the added acceleration. More specifically, the elevator's acceleration adds to gravity. So instead of just F equals mg, the total force becomes F equals m times the quantity g plus a. That's why the apple feels heavier. The spring is reacting to the extra acceleration on top of gravity. Most commercially available accelerometers work in this way, though it is integrated into a small device. Now, let's build a device. You can use any mass, but we picked one that gives us exactly 1 Newton of force, out of respect for Newton himself. Plus, we thought it'd be fun to show you what 1 Newton actually feels like. Since g equals 9.8 meters per second squared, to get 1 Newton of force, you need a mass of about 0.102 kilograms, or 102 grams. Looks like our apple is a little heavier than 102 grams, so it's pulling a bit more than 1 Newton. What can we do about it? Well, here's what we did. Now it's exactly 102 grams. So, you just learned that 1 Newton of force is about the force made by half an apple. Now the elevator. We go up from the ground to the 4th floor. If you look closely, zoom in, we held a 4-foot ruler against the window for scale. That ruler spans 177 pixels. The distance from the ground to the 4th floor measures 2,112 pixels. Since 4 feet is about 1.22 meters, we can calculate the building's height to be around 14.5 meters. We were careful enough to double check the height another way, by taking the stairs. There are 83 steps total to the 4th floor. Assuming each step is the same height, and we measured that to be around 17.5 centimeters, that gives us 17.5 centimeters times 83 steps to get 14.5 meters. Same result as the pixel method. Always good to verify with more than one approach. Alright, time for the experiment. We've got the apple suspended on a spring scale, just chilling in the elevator. Let's zoom in and take a closer look. Now, the doors close, and the elevator starts going up. See that? The apple gets pulled down a little bit, just for a moment. This is what acceleration looks like. When the elevator comes to a stop, the opposite happens. The apple moves up slightly, because the elevator has to slow down before it can stop. That slowing down is also acceleration, just in the opposite direction. Now here's where our expertise comes in. We wrote a code to track moving objects in the video. In this case, we're tracking 2 fixed points on the scale, and 1 point on the moving spring. Watch closely. You can actually see the spring bouncing up and down as the elevator moves. So the full sequence goes like this. The apple dips down for a moment, stays steady while the elevator moves, and then rises a little when it stops. This is what you feel when an elevator goes up and stops, right? Now let's process the sensor data. We'll start with the theory. You probably know the formula distance equals velocity times time. If you keep velocity v for time t, the distance traveled is v times t, which is the area shown in this graph. But velocity can change over time, so you can check your speed every minute and add those small slices step by step. The total distance is still the area on this graph. Now, a slightly more advanced idea, acceleration. Velocity change equals acceleration multiplied by time. The velocity change is the area on this graph. Just like the distance is the sum of many tiny velocity pieces, velocity change is the sum of many tiny acceleration pieces. The area on the graph is the total change in velocity. This process of adding up lots of small changes is called integration, hugely important in physics and math. Newton and another scholar, Leibniz, independently developed this idea around the same time. Newton didn't just get hit by an apple, he built the tools to analyze its motion. With the theory set and the apple ready, let's run the numbers. Here is the acceleration we measured from the apple's motion. To figure out how far the elevator traveled, we start with acceleration and work up to velocity. We add up these small acceleration pieces to this point and plot the total here. That total is the velocity change at this moment. You do the same for the next step and plot the new total here. Repeat again. You don't need to recompute the whole sum. You can keep a running total. At each step, add the new acceleration slice to the previous total and plot it. That incremental update is how acceleration integrates into velocity. When the acceleration is near zero, you're adding almost nothing, so the running total barely changes and the velocity stays steady. Here's a new twist. When the acceleration turns negative, the running total decreases over time, meaning the velocity goes down. And yes, this is the whole velocity graph. These graphs make sense, right? The elevator accelerates and increases its velocity, then holds nearly steady, then decelerates and slows until it stops and the velocity returns to zero. Now that we have the velocity, we'll integrate it to find the elevator's height. Just as before, we add up the velocity pieces to this point and plot that running total on the height graph. We keep adding new pieces and plotting the running sum on the height graph. Because velocity stays positive, the integrated height keeps increasing. At the end, the velocity goes to zero. The elevator stops at the 4th floor. That final value is the height we wanted. Take a look at the graphs. Initial acceleration shows up as a gentle curve at the start. Then, velocity holds steady, so height rises as a straight line. And it slows down, another gentle curve to stop the elevator. Just like a car doesn't instantly reach cruising speed, an elevator takes time to speed up and slow down. That smooth change is what we're capturing here. Now it's time to check the result. See the result computed from our apple experiment. The calculated height is 16 meters. And, do you remember, we measured the floor height to be 14.5 meters. Not bad at all for a DIY accelerometer using a half-eaten apple. The purpose of this video was to show the basic principle behind acceleration measurement. So we'll stop here for now. But here's a question for the teachers and scientists. What do you think caused the error? We ran the same experiment from the 4th floor to the ground, and we got almost the same result, 16 meters. Our experiment is very repeatable. Actually, we now have a good idea of what caused the error, and we fixed it. Please pause here and think about it. In a follow-up, we can walk through the cause and show how the revised method changes the analysis.